So let's take a look at this example here, 4.6.2, for a perfectly elastic collision. Now we're going to consider the example problem 4.6.1 from earlier in the text where we're looking at an inelastic collision. And I'll reference that in a minute and give you an overview of that problem with the solution to reference back to. So we're now going to be talking about a perfectly elastic collision based on the figure shown below here. So we're going to suppose that mass, right here, our mass m1 is equal to m, and it's going to be moving with a speed of v1 towards this mass m2, which has a mass that's 10 times that of mass m1, which is m. So after striking it there, we're going to assume a perfectly elastic collision. From there, what they're asking us to solve for is an expression for the displacement x of t after our collision occurs. So here's the problem that they referenced at the beginning of 4.6.2. This is 4.6.1, the previous problem, example problem in our textbook here, for an inelastic collision. So shown here, again, same type of situation. We have an m1 and m2 here. Initial velocity of m1 is v1. They give us all this information here. m1 is equal to m. Moving with the speed of v1 becomes embedded in mass m2 after striking it, which we can see down in the figure shown here. We can suppose that m2 is equal to 10m, and they want us to determine an expression for displacement xt after the collision. Here's our solution for this for an inelastic collision. Just wanted to reference back to that because they're saying we're going to expand upon this problem in 4.6.2, but do it for a perfectly elastic collision. So now going back to our solution for 4.6.2, first thing we want to do is create our setup page. We have this perfectly elastic collision. We have our m1, known mass m, going at a velocity v1, coming into contact here, colliding with m2, which is a mass of 10 times that of m1. We have our spring constant here, k, and our distance moving in our direction here of x. So I write down all my known variables. m1 is equal to m, v is equal to the velocity of m1, and m2 is equal to 10 times the mass of m1, or 10 times m. So we want to find an expression for the displacement after the collision occurs, looking for our x of t. Our assumption is that it's going to be a perfectly elastic collision. So that'll be the difference between this example here and the previous example in our textbook. So as we begin our solution for this problem, we want to let v3, for our variable name, be the velocity of mass m after the collision. So our key equation that we're going to use here references back to our textbook 4.6.7 in the 4th edition, where v3 is going to be equal to our m1 at mass 1 minus our mass 2, all divided by m1 plus m2 times our velocity here, v1. So our initial velocity there. So for our particular case here, this simplifies down because we know that m2 is equal to a mass of m, and m1 is equal to a mass of m, and m2 is equal to 10 times that mass there. So we have a relationship between m1, m2, and our mass m. So we can plug those back into this equation 4.6.7. We do that here. We see that v3 is equal to m minus 10m, because m1 is m, m2 is 10m, all over m plus 10m times our v1. So we can simplify this down. M minus 10m becomes a negative 9m, and m plus 10m becomes 11m. So we have this negative 9 over 11 times our velocity 1 is our velocity 3. So v3, we have a ratio now relating it back to v1. Now if we think about this velocity, one thing to check out is, okay, we're moving to the right in what we're considering our positive x direction initially, so we have a positive velocity v1. When it rebounds, it's going to be going back in the opposite direction, and we see a negative here. So that is a great double check with sign convention to make sure, okay, does that make sense? Is v3 really moving in the opposite direction of v1? In this case, yes. Yes, it is. That's a great double check. So for the next part of our solution, we're going to be looking for the change in the momentum of m, our mass. So we can use our impulse momentum principle, which we can reference back to section 4.6 in our textbook. And if you have the 4th edition, that's equation 4.6.1. So this impulse momentum principle in general form is m times v of t minus m v of our initial condition here for impulse is equal to the integral of fu du. So this is in general terms. Now from Newton's second law, we know that ma is equal to ft, or mv dot is equal to our f of t here. So what we can do here is we can rearrange a little bit. So mass times the change in velocity equals the force equation with respect to time. So we can plug this relationship back up to our impulse momentum equation up there. We can get the following here. Now we have mass times v3 minus mass times v1 is equal to the integral of ft dt, or our difference in velocities here, delta t, or our v dot, is the change in velocity. Acceleration is a change in velocity with respect to time, so our change in velocity is the difference in our two velocities there. So we can do that there, and what we see now, we plug in our v3, we have the relationship we just solved for, relating it back to v1. So the mass times v3, which is negative, going opposite direction, 9 over 11 times v1, minus the mass times v1, which is just given to us as v1, is equal to the integral of ft dt. So now we've plugged in there, again, from Newton's second law and our impulse momentum principle here, we now have an expression here relating our masses and velocities and forces. So if we rearrange that a little bit for our linear impulse applied to the mass m during the collision, we get the following here. We have the integral of ft dt is equal to negative 20 over 11 mv1. So let's think back now to Newton's law of action and reaction. So we have linear impulse applied to the 10m mass is equal to here 20 m1 v1 over 11 here, on the right hand side of this equation up there. So from our equations of motion with no damping, we have the general form here, mx double dot, mass times acceleration, the second derivative of position with respect to time, plus kx, our spring constant k, times our distance x here, is equal to function f of t for force. So we can plug into this equation with our known values here, and we get the following. So we have here for us, this is 10 mx double dot plus kx is equal to, now we have a right-hand side of the equation, again, from Newton's law of action reaction up here, and Newton's second law here from linear impulse, we have 20 over 11 times m1 v1 times delta t here. So now we have a right-hand side of our equation. We have our equation motion for our specific one with our mass of 10 over here. So now we have this relationship here. So why do we really want to get it in that form? Well, that's the form here we're used to when we're dealing with Laplace transform. So we have an ordinary differential equation here that we've just derived up to this point here, and now we can have fun and do some Laplace transform. So this will be a little bit of a refresher for how we can apply this to a simple ODE here. So if we recall, we can look up various general form solutions for Laplace transforms off of tables. You can use different numeric solvers to get there, but let's just go from the tables here. So we have our general solutions for some of these different Laplace transforms. So we have f, plus of that is going to be f of s here, capital F of s, df dt, first time derivative of our function f here, our f variable, is equal to s times f of s minus f, lowercase f of 0, which is an initial condition. And if we have the second derivative here, d squared f dt squared, we end up with s squared times capital F of s minus s times our initial condition here, f of 0, minus the initial condition over here, the derivative of f with respect to time, at 0. So our initial conditions are coming into play when we're dealing with first time derivative of f, second time derivative of f here. Or in our case, let's sub in for x and use our general notation for Laplace. So if we have the Laplace of x, what we end up with, capital X of s. If we take the Laplace transform of x dot, or our first time derivative here of x here, what we end up with is s times capital X of s minus x naught, where this is an initial condition. If we take the Laplace of x double dot, or our second time derivative here of our function of x here, we end up with is s squared times x of s minus our initial conditions there, s of x naught minus s of x dot, not over here, our initial conditions there, where these are given to us in the problem statement. So we have values that we can plug in for these. So now we go back to that equation. Now that we've done a little bit of review of Laplace transform, pulling these off a table for general form here, we can go back to our differential equation here, 10m x double dot plus kx is equal to our right-hand side of our equation over here, 20 over 11 times mv1 delta t. Well, we go back up here to our general table and we can see here, okay, we're dealing with this and this. Or, for our specific problems, this here and this bottom one here. So we have second time derivative and then we just have our function x here. So we can deal with those individually. To write this all out, let's just deal with the left-hand side of the equation first. So take the Laplace of 10m x double dot plus kx. And what we end up with when we do that is we can separate this out and deal with it just in terms of our x double dot expression and our x expression based off of these two here. So that's what we'll do next. So I'll read out right at the top of the page here just so we can quickly reference to it on this page here. Laplace of our function here, our ordinary differential equation here, 10m x double dot plus kx. And there's a right-hand side of the equation that we've already taken Laplace of is 20 over 11 times our mv1. So all we have is our constants out front of that there. There was nothing in terms of x there, so we're all set. So now we have to pull out our constants and break up our left-hand side of the equation here. So I can see I have a 10m here and I have a k here. So I'm going to pull that out. So for the first part of this, I have 10m times the Laplace of our x double dot with respect to s here, plus I have my k pulled out front here as my constant out front of the Laplace of our x there is equal to our right-hand side of the equation. So now we know we can reference back to the previous page or our table. We have solutions for both of these here in general terms. So we can write that out. We know the solution for this guy here is s squared capital X of s minus our initial condition x naught and x prime or x dot naught here. So our initial condition when time is equal to 0 for x, initial condition when time is equal to 0 for our x dot. Plug those values in. Well, those are both zeros, and we plug those in given to us in the problem statement. So both of those terms go away. This is added to our k times our x of s over here from this guy right here, our general form for Laplace here. So this ends up just being equal to our right-hand side of the equation of 20 over 11 times mv1. So we can reduce and simplify. Again, these two terms will go away. Reduce this down here, and we end up with, when I distribute my 10m through this, we end up with 10ms squared xs plus k times xs here equal to the right-hand side of the equation 20 over 11 times mv1. Well, we can pull out this x of s here, capital X of s there, plug this in on the right over here. So now we can say 10ms squared plus k times this capital X of s here is equal to the right-hand side of the equation 20 over 11 times mv1, where now we can go through and solve for this x of s here, capital X of s. So we do that there. X of s is equal to 20 mv1 over 11 divided by 10m s squared plus k. So now we have an expression here for capital X of s. We remember, if we go back to our initial problem statement, our setup page there, we're looking for lowercase x of t here. So in order to do that, we're going to end up doing our inverse Laplace. But before we want to apply that, let's reduce and simplify this mess right here a little bit. So we want to simplify down this expression here. 20m v1 over 11 divided by 10ms squared plus k. What I'm going to do here is I'm going to pull out a 20m here and a 10m here on both the numerator and the denominator. So 20m here, that's going to be times our v1 over 11. If I pull out a 10m here, that's going to be times an s squared and times a k over 10m there. That way we just have k when we distribute that through. The reason we want to do this is we can cancel out an m that way and reduce this to 2 over 1 rather than 20 over 10. We do that here, we now have an expression for capital X of s equal to 2 times v1 over 11 times 1 over s squared plus our k over 10m there. So now we're set up in a position where we can do an inverse Laplace transform. And the reason I want this out front here is so I can get this into a simplified form and call this an a and a b here, because these are both constant values. So I'm going to rewrite this in this general form down here of a times 1 over s squared plus b, where a and b are both going to be constants. Different constants, but both going to be constants. So off to the right, I'm going to set these aside and say a is equal to my 2v1 over 11, my a, and b is equal to my k over 10m right there. So two constants right there off to the side. Gets this into a simplified general form that I can go to a lookup table for. So from that table, I can see x of t is the inverse Laplace of this a times 1 over s squared plus b. Well, the general form here for the inverse Laplace transform of that function is a times 1 over the square root of b times the sine of the square root of b times t. So I can plug in my a's and b's now up here for my specific problem once I found that general form solution there. So x of t is equal to 2 times v1 over 11, my a, times 1 over b, which my b was k over 10m I plug in here, times the sine of my b, k over 10m, times t. I can rearrange, simplify that just a little bit. We end up with x of t is equal to 2v1 over 11 times the square root of 10m over k times the sine of the square root of k over 10m times t.